Welcome to Understand the Math. In this Calculus 1 video, we're tackling one of the most fundamental ideas in all of calculus, continuity. We'll talk about what it means for a function to be continuous, look at different types of discontinuities, explore how continuity works on intervals, and then look at its connection to the Intermediate Value Theorem. Be sure to download the free guided notes to help you follow along step by step. Let's start by looking at continuity definitions and then walk through an example. The first definition that we're going to look at tells us what the three conditions are for a function to be continuous. The function that I've drawn here on the right is an example of a function that is continuous. Our definition tells us that a function f of x is continuous at a number x is equal to a, over here on our graph, if three requirements are met. The first one is that the function at point A has to exist. In our graph, we can see that our function does exist at point A. Our second condition tells us that the limit as x approaches a of f of x exists. In our graph, we can see that the limit exists because the limit from the left is equal to the limit from the right. Our third condition then tells us that both conditions 1 and 2 have to be equal. Looking over here at our graph on the right, our function value is equal to our limit. So this function is continuous. Our second definition talks about continuity from the left. Our graph over here on the right shows a function that is continuous from the left. A function f of x is continuous from the left if the limit as x approaches a from the left is equal to our function value at a. Let's now talk about continuity from the right. This graph here on the right is a graph of a function that is continuous from the right. A function is continuous from the right if the limit as x approaches a from the right is equal to f of a. We'll do some examples of all three of these in just a little bit. Our fourth definition is about discontinuity, and it tells us the three ways that a function can be discontinuous. A function f of x is discontinuous at a number x is equal to a if it is not continuous there. So basically, wherever a function is not continuous, it is discontinuous. Let's now look at these three graphs I have right below our definition. The graph on the left has a function that is discontinuous because the function does not exist at the point x is equal to a. There is an open circle there. Let's now look at our graph in the middle. In this graph, our function exists at the point a, but the limit of f of x as x approaches a does not exist. So what's happening is at a, the limit as x approaches a from the right is not equal to the limit as x approaches a from the left. Let's now look at our graph on the right. This graph also represents a function that is discontinuous. For this function, f of a exists. That's that point right there. The limit exists because the limit from the left is equal to the limit from the right. But these two values are not equal to each other. This value is different than that value. So our function is discontinuous. Let's now look at an example. In part A, we are going to state the values of x at which our function f is discontinuous and then explain why. In part B, at those numbers where our function is discontinuous, we are going to determine whether our function is continuous from the right, from the left, or neither. A function can be discontinuous at a point, but still be continuous at that point from the left or from the right. Let's see how this works. We'll begin with part A. Let's start by looking at our x values as we go from left to right. Here's the first x value that we're going to look at. If you look up at our graph, notice that our function value has an open circle at that point, and that means our function is discontinuous. So we're going to say that at x is equal to -4, f of -4 is undefined. And that's why our function is discontinuous. Let's now look at x is equal to -2. At this point, our function value exists. However, the limit from the left does not equal the limit from the right. So let's go down here and let's write x is equal to -2. The limit as x approaches -2 of f of x does not exist. Now let's go to our next point. That's going to be the point 2. At this point, our function value exists, but again, the limit from the left does not equal the limit from the right. So it's discontinuous at that point. We'll write down x is equal to 2. The limit as x approaches 2 of f of x does not exist. Let's now look at our last point. That is x is equal to 4. For this point, our function exists. However, the limit from the left does not equal the limit from the right. So we'll write down x is equal to 4. The limit as x goes to 4 of f of x does not exist. Sometimes you can write does not exist as D and E, and that will make things a little bit quicker. Let's now go to part B. We'll pull this up so we can see. For part B, we wanted to know at these numbers, that's -4, -2, 2, and 4, if f is continuous from the right or from the left or neither. We'll see if we can squish B in right here. So at x is equal to -4, we need to look at our function. Because there is an open circle at that point and no closed circle, our function is not continuous from the left or from the right. So we're going to write down neither. Let's look at our next point. X is equal to -2. At -2, let's go up here and look at our graph. Notice that as we approach from the left, our left-hand limit is equal to our function value, so it is continuous from the left. So let's go down here and let's write left. Now we go to x is equal to 2. Let's go back up to our graph and look at 2. Our function value is defined here. This limit is equal to the function value, so it is continuous from the right. So we'll put right down here. And then our last one, x is equal to 4. Let's go up here and look at our graph and see what's going on at 4. Here's our function value, and the limit that is equal to it is the one coming from the right. So just like x is equal to 2, at x is equal to 4, our function is continuous from the right. I hope this makes this problem clear. I know when I used to teach this problem in class, this was one that students really struggled with and had to go over a couple of times. Let's now look at 3 ways that a function can be discontinuous and walk through some examples. The first type of discontinuity that we're going to look at is called a removable discontinuity at a point x is equal to a. A removable discontinuity occurs at a point where a function's limit exists, but the function's value at that point is either undefined or doesn't equal the limit. And this creates what we call a hole in the graph. In example 1, we have a function that has a removable discontinuity, and we're going to look at it and see exactly why it has a removable discontinuity and where that discontinuity is. You can see that the denominator is going to equal 0 when x is equal to 2, so our function is going to be discontinuous at x is equal to 2. Let's just write down here x is equal to 2, so we know that's where it's going to be discontinuous. To understand why this is called a removable discontinuity, let's look at our function and see if we can simplify it. The numerator of f of x can be factored, and let's go ahead and let's do that. We can factor this as x plus 1 and x minus 2, and that all gets divided by x minus 2. Notice that the x minus 2 on top is going to cancel out with the x minus 2 on the bottom, and this function can be written as x plus 1. Because we factored out an x minus 2 from the denominator, we can say that our function has a removable discontinuity at x is equal to 2. And we get that x is equal to 2 by just setting x minus 2 equal to 0, and we get x is equal to 2. Let's now graph this function so that we can understand it a little bit better. This function is going to be a straight line given by this. It is going to pass through the point 0, 1 and have a slope of 1, so we can go ahead and graph it like this. Now, here's where we have to be careful. Our function is not exactly x plus 1. It reduced to x plus 1, but our function is this function right up here. And this function has a discontinuity at 2, so we need to put a circle right here to denote that our function is not continuous at that point. Let's now look at another example. This is an example that also has a removable discontinuity, but it's a little bit different. Let's start by rewriting our function. Notice that, let me pull this down. Notice that this is the same function that we had before, so we can go ahead and write it as f of x is equal to x plus 1 when x is not equal to 2, and it's equal to 1 when x is equal to 2. It's going to be just like our function above, except now it's going to be defined to be equal to 1 when x is equal to 2. Let's graph this function. When x is 2, our function is 1. So let's put in a closed circle right here. And then the function is going to look exactly the same as it did before, except now we're going to have an open circle here. So it's going to look like this. Our function is discontinuous at x is equal to 2, and this is called a removable discontinuity at x is equal to 2. Before we go on, let's relate this problem to our definition of continuity. The value of our function at 2 is equal to 1, and the limit of our function as x approaches 2 is equal to 3. We can see that up here on our graph as we go from the left and from the right, we arrive at a value of 3. Notice that 1 is not equal to 3, so f of 2 is not equal to our limit as x approaches 2 of f of x. And our function is not continuous at x is equal to 2. Let's now look at our second type of discontinuity. It is called an infinite discontinuity. An infinite discontinuity occurs at a point where the function's value approaches positive or negative infinity from at least one side, creating a vertical asymptote. Down here, we have an example of an infinite discontinuity. When we set the denominator of this function, x minus 3 quantity squared equal to 0, we get x is equal to 3. So at the point x is equal to 3, our function is undefined. If we will look at the limit, as x goes to 3 from the right and the left, I'm doing both of them combined because x minus 3 is squared, of 1 over x minus 3 quantity squared, we get approximately 1 divided by 3 from the right or left minus 3 squared. And this is approximately 1 over 0 from the right or left squared, which is approximately infinity. So our function is approaching positive infinity from the left and the right side of x is equal to 3. This means we are going to have a vertical asymptote at x is equal to 3, and our function is going to look like this. This type of discontinuity is called an infinite discontinuity. Algebraically, f of x can have an x minus a in the denominator that can't be factored out. And that leads to an infinite discontinuity and then also to a vertical asymptote at x is equal to a. If the x minus a can be factored out, then it's a removable discontinuity. But if it can't be factored out, then it is an infinite discontinuity. Let's now look at the third type of discontinuity, and it's called a jump discontinuity. A jump discontinuity occurs when a function's one-sided limits at a specific point both exist, so that means the limit from the left exists and the limit from the right exists, but here's the catch, they are not equal. And when that happens, there is a break in the graph and the function jumps from one value to another. Here's an example of a function that has a jump discontinuity. To understand how this function has a jump discontinuity, let's look at the absolute value of x minus 2. I'm first going to write down a definition that you need to know, and in case you haven't seen it, here it is. The absolute value of x is defined to be x when x is greater than or equal to 0 and minus x when x is less than 0. We are going to use this as a guide to write down what the absolute value of x minus 2 is equal to. That is equal to x minus 2 when x minus 2 is greater than or equal to 0, which just means that x is greater than or equal to 2, or minus the quantity x minus 2 when x is less than 2. When we substitute this value into here and then this value into here, here's what we get. We get that f of x is equal to 1 when x is greater than or equal to 2, or it's equal to minus 1 when x is less than 2. You can then see that the limit as x approaches 2 from the right is equal to 1, and the limit as x approaches 2 from the left is equal to negative 1, and those two values are not equal. So our function has a jump discontinuity at x is equal to 2. When x is greater than or equal to 2, our function is equal to 1. So let's put a closed circle here and a line here. And then when x is less than 2, our function is -1. So we'll put an open circle here and a line here. You can see then that this function is discontinuous at 2, and it is a jump discontinuity. We're going to now look at some examples where we are going to state where our function is discontinuous and then state the type of discontinuity. In our first example, we are going to be looking at this graph. There is a lot to that graph. I think the best way to approach this problem is to start looking at this graph and see where it is discontinuous, and we'll start looking at the points on the left and then move to the points on the right. The first point that we're going to look at is x is equal to -2. At x is equal to -2, the function exists and the limit exists. However, these two values are not the same. So we're going to say that at x is equal to -2, we have what's called a removable discontinuity. It is not a jump discontinuity because when we have a jump discontinuity, the value starts at one value, goes to the next value, and then continues on from that value. With this one, our function only jumps at a single point. So it's called a removable discontinuity. Let's now look at our next x value, and that is x is equal to 2. Notice at x is equal to 2, our function is defined. However, the limit from the left is different than the limit from the right. And that tells us that we have a jump discontinuity. At x is equal to 2, let's write down that we have a jump discontinuity. Now let's look at what's happening when x is equal to 4. Our function is not defined at x is equal to 4, and our limit from the left is going to infinity, and our limit from the right is going to infinity. So at x is equal to 4, we have what's called an infinite discontinuity. Now let's look at our last point. That is at point 6. You might want to pause the video and see if you can determine what type of discontinuity we have here. Our function is defined at x is equal to 6, but the limit from the left does not equal the limit from the right. And that means just like when x is equal to 2, we have a jump discontinuity. So we'll write down x is equal to 6. We have a jump discontinuity. Let's now look at our second example. In our second example, we see that the function is defined at x is equal to 1. And to determine the type of discontinuity, we need to understand better what's happening in the region around x is equal to 1. So let's look at the limit as x approaches 1 from the left of 1 over x minus 1. This is approximately 1 divided by 1 from the left minus 1. So this is approximately 1 divided by a number like 0.99 minus 1. So this is going to be 0 from the left, and that's going to be minus infinity. Now let's look at the limit as x approaches 1 from the right. This one's easier. This is 1 over x minus 1. This is approximately 1 divided by 1 from the right minus 1. Think of this as 1.0001 minus 1. So this is 1 divided by 0 from the right. And this is positive infinity. Because our limits are infinite, we have an infinite discontinuity at x is equal to 1. So let's write down infinite discontinuity. I'm just going to abbreviate that at x is equal to 1. Let's go ahead and let's graph this just so that we can better understand it and see what it looks like. We have an infinite discontinuity at x is equal to 1, so we'll put a vertical asymptote there. And then at 1, our function is equal to 2, so we'll put a closed circle here. As we approach 1 from the left, we're going down to negative infinity. So our function's going to look like this. And as we approach 1 from the right, it's going to go up to positive infinity. Later on in this course, we're going to be talking about horizontal asymptotes, which we really need, honestly, to be able to understand this graph a little bit better. But for now, I just wanted you to see the graph so that you can see what it looks like when we have an infinite discontinuity. Let's now look at example 3. This one is a little bit more complicated, but just like our second example, our function is defined at x is equal to 1, and now we have to figure out what's going on at a region near 1. Let's take our complicated function when x is not equal to 1 and see if we can maybe factor it. Let's take x squared minus x, all divided by x squared minus 1. We can definitely factor it. In the top, let's pull out an x, so we have an x minus 1. And in the denominator, we can factor that as x plus 1 and x minus 1. Now let's notice that these two terms cancel out, and we can write this as x all divided by x plus 1. Because we canceled out an x minus 1, what we can do is we can take x minus 1, set it equal to 0, and solve for x, and we get x is equal to 1. This means at x is equal to 1, we have what's called a removable discontinuity because we were able to remove that from our function. Now let's look at the function that we have left. Notice that there's an x plus 1 in the denominator. Let's take that and let's set that equal to 0. And that gives us x is equal to minus 1. When x is equal to minus 1, our denominator is going to go to 0. So our function is going to go to infinity and also to minus infinity. Let's go down here to the bottom and write down then at x is equal to negative 1, we have an infinite discontinuity. And I'm going to go ahead and I'm going to highlight these answers. We have a removable at x is equal to 1, and we have an infinite discontinuity at x is equal to minus 1. Let's go ahead and let's graph this function just so that we can better understand this. At negative 1, we have an infinite. So that means we're going to have an asymptote there. Our function actually has a horizontal asymptote at y is equal to 1. Again, there's no way that you would know that at this point. Just take my word for it. And then we have on the right-hand side of our asymptote, our function's going to go down like this. It does pass through the origin, and it's going to go over like this. And then at x is equal to 1, it's defined to be 1, so we're going to put a closed circle there. And we're going to put an open circle right there. So you can see from the graph, we have an infinite discontinuity at x is equal to minus 1 and a removable discontinuity at x is equal to 1. Let's now look at our fourth example. This example is a piecewise function, so we're going to start by looking at the limit of this function as we approach 1 from the left and from the right. Let's first look at the limit of f of x as x approaches 1 from the left. That's right here, so we're going to look at that piece right there. So this is the limit as x approaches 1 from the left of 1 plus x squared. Plug in x is 1, so we just end up with 2. Now let's look at our right-hand limit. The limit as x approaches 1 from the right of f of x is the limit as x approaches 1 from the right of 4 minus x. Now we're grabbing this piece, plugging in x is 1, and we end up with 3. Notice that the limit from the left is not equal to the limit from the right, and it doesn't go to infinity, so this tells us that we are going to have a jump discontinuity. At x is equal to 1. Let me graph this for you just so that you can see this better. When x is equal to 1, we found that our function is equal to 3. So I'm going to put a closed circle right here. We'll mark this point 1. To the right of 1, our function is 4 minus x. That means it is going to have a slope of -1, and it's going to look like this. If we look at the first piece in our function, when x is less than 1, we plug in 1, we see that we got 2. So we're going to have an open circle here at 2. And then our first function is a parabola, and it's going to be shaped like this. Don't stress about the graphs for now. I just want you to see the graph so that you can see that we do have a jump discontinuity at x is equal to 1. We're going to now look at an example where we're asked to find the value of a constant c that makes f of x continuous everywhere. The first piece of our function and the second piece of our function are both polynomials, which means they are going to be continuous everywhere. If our function is going to be discontinuous, it is going to be discontinuous at x is equal to 3. Now, I think what we can do is find a value of c where it is not discontinuous. In order to do that, what we're going to have to do is we are going to have to set the first piece of the function equal to the second piece of the function and plug in x is equal to 3. Let's go ahead and let's do that. We have c times 3 cubed minus 6 is equal to 4 times 3 squared plus 2c times 3. Now we have to solve for c. Let's clean this up a little bit. On the left, we have 27c minus 6. And on the right, we have 3 squared, which is 9, times 4 is 36, plus 2 times 3 is 6, so we have a 6c. Let's move the c's to the left and the constants to the right. So we have 27c minus 6c on the left and 36 plus 6 on the right. 27 minus 6 is 21. So we have 21c is equal to 36 plus 6, which is 42. And that works out real nice. Dividing by 21, we see that c is equal to 2. So we can conclude that our function is going to be continuous even at x is equal to 3 if c is equal to 2. We're now going to talk about how a function that is not continuous everywhere can be continuous on a certain interval. There is a theorem that states that the following functions are continuous at every point in their domain. These are polynomials, rational functions, root functions, exponential and logarithmic functions, as well as trigonometric and inverse trigonometric functions. All of those functions are continuous at every point in their domain. Our job then, when we see these functions and combinations of these functions, is to determine what the domain of these functions should be for them to be continuous. Just as a guide, we can say that a function may fail to be continuous at points where the denominator equals 0, an expression inside a square root is negative, and an argument of a logarithm is less than or equal to 0. A square root is only defined for a function that is greater than or equal to 0, and a logarithm is only defined when what is inside the logarithm is greater than 0. Not even equal to 0. It has to be greater than 0. We're going to look at some examples, and we are going to determine the intervals on which our function is continuous. Let's look at our first example. Notice that we have a denominator equal to x plus 1. Our function is not going to be continuous when that denominator is equal to 0. So let's take x plus 1 and let's set it equal to 0, and we get x is equal to negative 1. So our function is not going to be continuous at x is equal to negative 1. The trigonometric function sine x is always continuous. Now what we need to do is find the intervals on which our function is continuous. I think the easiest way to do that is to just draw a number line. We'll label this as x, and we're going to take x is equal to negative 1, and we're going to put a big X right there. X cannot be equal to negative 1. So the intervals on which our function is continuous are going to be from here to here, and then from here to here. So our solution is our function is continuous on the intervals minus infinity to minus 1, union minus 1 to infinity. Now let's look at our second example. We're going to focus on our square root. We talked up above about our square root being only defined when what is inside the square root is greater than or equal to 0. So we are going to set x minus 4 greater than or equal to 0. So we get x is greater than or equal to 4. The other piece of our function is a polynomial, and it is always continuous. Let's go ahead now and let's do our number line. We'll label it as x. We're going to put the point 4 here, and we're going to denote that x has to be greater than or equal to 4. So we're going to put a square bracket here and an open bracket over there at infinity. Our answer then is our function will be continuous on the interval from 4 to infinity, and we have a closed bracket at 4. Now let's look at our third example. We'll look at our natural log function first. A natural log is only defined if what is inside the natural log is greater than 0. So we're going to set x minus 1 greater than 0, and that's going to give us that x has to be greater than 1. Now let's look at our denominator. We cannot have a denominator be equal to 0, so we're going to require that x squared minus 4 is not equal to 0. Solving this, we get x squared is not equal to 4, which means x is not equal to plus or minus 2. Don't forget the negative piece. Now let's go ahead and let's draw our number line. We're going to have more to put on this one. Let's see here. Let's put the point 1, and then we're going to put the point minus 2 and 2. Now let's see what's going on here. X cannot equal negative 2 or positive 2, and then x has to be greater than 1. So we're going to put an open bracket here. It can't equal 2, so we're going to put open brackets around 2 and then a bracket here at infinity. So our answer is that our function is continuous on the interval from 1 to 2, union 2 to infinity. Let's now look at the intermediate value theorem and walk through some examples. Here's the main idea of the intermediate value theorem. If you have a continuous function that goes from one value to another, it must pass through every value in between. I've written the intermediate value theorem here in our green box, and we're going to go through it and at the same time look at our graph so that we can better understand it. Our intermediate value theorem has a condition, and that condition is that our function is continuous. In other words, our theorem only applies to continuous functions. If our function is continuous on the closed interval from a to b, looking down here at our graph, we are going from x is equal to a to x is equal to b, and n is any number between f of a and f of b. I've already highlighted it down here, and it lies between f of a and f of b, and those two functions can't be equal. Then there exists a number c, which I've highlighted right down here, in the interval between a and b, such that f of c is equal to n. Let me tell you exactly what this means. All this means is if all these conditions are met, then we have a number n that's equal to f of c that can take on every value between f of a and f of b. Let's now see how this works in practice and walk through two examples. One really nice application of the intermediate value theorem is when we can use it to show that an equation has a root in a specified interval. And that's what our examples are going to be about. In our first example, we are going to use the intermediate value theorem to show that there is a root of the given equation in the specified interval. Let's talk at first about what a root is. A root of this equation is just a point x where x cubed minus x minus 2 is equal to 0. So basically, when we solve this equation, we are just finding the roots. I have graphed this equation so that we can better understand this. What we are looking for is to show that we have a root of this equation. So that is going to be this point right here, where our function x cubed minus x minus 2 is equal to 0. And we want to show that we have a root between x is equal to 1 and x is equal to 2. To show this, we are going to look at our function values at 1 and at 2. F at 1 is equal to 1 cubed minus 1 minus 2, which is just minus 2. And let's make a note that that's less than 0. And then f of 2 is 2 cubed minus 2 minus 2, which is 8 minus 4, is equal to 4, which is greater than 0. Because f of 1 is less than 0 and f of 2 is greater than 0, the intermediate value theorem tells us that there has to be a number c such that f of c is equal to 0, because our function has to take on every value between -2 and 4, and 0 lies between -2 and 4. So by showing that f of 1 is less than 0 and f of 2 is greater than 0, we've basically shown that the intermediate value theorem will guarantee that we have a root between 1 and 2. Let's now look at our second example. This example is similar to our first example, but a little bit more complicated because we are not given an interval. In this problem, we are asked to show that there is a root to this equation. We are going to solve this problem in 2 steps. Our first step, we are going to create f of x. Because we want to find a root to this equation, our function f of x is going to correspond to f of x is equal to 0. So if we go up here and look at our equation, we can write this as the square root of x minus 5 minus 1 over x plus 3 is equal to 0. And this is our f of x. Let's go ahead and write that down. F of x is equal to the square root x minus 5 minus 1 all divided by x plus 3. Now what we're going to do is we're going to find f of a and f of b, because those two quantities are used in the intermediate value theorem, and that's the theorem that we're going to use to show that we have a root to the equation. Now, we are not given a and b, so where do we start? I think the best place to start is to look up at our function and see that we have a square root, and we're going to have to require that anything inside our square root is greater than or equal to 0. So that's where we start. We are going to set x minus 5 greater than or equal to 0, and that tells us that x has to be greater than or equal to 5. We now need to choose an a and a b, and it has to be greater than or equal to 5. I am going to let a be equal to 5, and let's see what happens. F at 5 is the square root of 5 minus 5 minus 1 divided by 5 plus 3. So this is equal to minus 1 over 8, and let's make a note that that is less than 0. Now we need to choose a b. We just need to pick a number that's bigger than 5. Notice that the answer that we just got was minus 1/8. That's really close to 0. So I have a guess that we could make b be equal to 6, and we might get a function that's bigger than 0. Let's see what we get. F at 6 is the square root of 6 minus 5 minus 1, all divided by 6 plus 3. This is 1 minus 1/9, and this is equal to 8 over 9. Let's highlight that. This number is greater than 0, so this is great. We found that f of 5 was less than 0, and f of 6 was greater than 0. So this tells us by the intermediate value theorem, let's write that down, we'll abbreviate it as IVT, there is a root to this equation, and let's put in parentheses that that root is where f of x is equal to 0, since f of 5 is less than 0, and f of 6 is greater than 0. The intermediate value theorem tells us that our function is going to take on all the values between f of 5 and f of 6, which means it's going to take on the value of 0, which is a root to our equation. And that's it. You've seen what it means for a function to be continuous, the different types of discontinuities, how continuity works on intervals, and how to apply the intermediate value theorem. To really master these concepts, make sure you work through plenty of practice problems on your own. That's really the only way to learn calculus.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.